When we look out at the universe, it feels kind of familiar, right? We've got our regular stars, the ones powered by fusion. We've got their corpses, these super dense neutron stars, and of course the ultimate cosmic monsters, black holes where gravity just wins, period. For a long, long time, we figured, hey, that's pretty much the whole cast of characters.
I mean, for ages, the story of a giant star always ended the same way. It burns out, collapses, and if it's massive enough, poof, it becomes a black hole. An object with gravity so powerful that nothing, not a single thing, not even light itself, can get away. It was, for all intents and purposes, the end of the line.
But what if that's not the whole story? What if there's a whole other collection of bizarre, exotic objects out there? A kind of cosmic zoo, hiding in the shadows, that could just rewrite everything we think we know. Well, that's the hunt we're on today.
So let's step into the universe's hidden zoo. Now, this isn't about lions and tigers. No, this is a hunt for hidden stars. These theoretical objects that the laws of physics say could exist, even if we've never actually laid eyes on one. Yet.
You should really think of this more like a cosmic detective story than traditional astronomy. We've got a list of suspects, and every single one is predicted by physics when you push the laws to their absolute breaking point. And we're not talking about just slight variations of stars we already know. Oh no, these are fundamentally different kinds of beings.
All right, so who are the main suspects in our cosmic investigation? Let's take a look at the frontrunners. These are the exotic stars that scientists think we're this close to discovering. We could be talking in the next few years even.
Okay, suspect number 1 is the dark star. Now, that name is a little deceptive. They wouldn't have been dark at all. In fact, they would have been unbelievably bright, absolute giants in the early universe. What set them apart was their engine. See, their furnace wasn't nuclear fusion like our sun. It was powered by the annihilation of dark matter. And the differences here are just mind-boggling. See, instead of burning hydrogen, dark stars would have fed on dark matter particles inside the super-dense halos of the very first galaxies. And that fuel source, it burned way slower and more gently than fusion. That meant less outward pressure, which let them just swell up to become millions of times more massive than our sun, all before the universe had even cooked up any heavy elements.
And hey, this isn't just some fun idea. The hunt is on. Right now, as we speak, the James Webb Space Telescope is basically the perfect detective for this case, because it can peer back to the dawn of time. And guess what? It's already found some things out there that are, frankly, way too big and way too bright to be normal early stars. So right now, scientists are poring over their light looking for a very specific helium signature that would be the absolute smoking gun.
So when you put it all together, you've got a solid theory, you've got the perfect tool for the job with JWST, and you've already got some very intriguing candidates. It's pretty obvious why dark stars are our #1 suspect. The case is building, and a discovery could be right around the corner.
Okay, next step in our lineup of heavy hitters, we've got hybrid and quark stars. So what happens if you take a neutron star and just crush it even more? Well, some theories say the neutrons themselves would actually break down, dissolving into this suit of their fundamental building blocks, quarks. This would create a whole new state of matter, either as a pure quark star or as a hybrid star with a quark core hiding inside a neutron shell.
So this kind of gives us a clear roadmap for the whole hunt. As you can see, dark stars are the 5-star favorite, all thanks to the incredible power of the JWST. But hybrid and quark stars are right on their heels. We've got instruments like NICER, which is measuring the size of neutron stars with insane precision, and our gravitational wave detectors like LIGO. They're all closing in on the evidence we'd need to say, yep, they're real.
Okay, so those were the favorites. But now we're going to venture a little deeper into the zoo. It's time to meet the ultimate outsiders. These are the long shots, the ones that could bend reality itself. Finding one of these would change, well, everything. First up, boson stars. And these things are just weird. They're made of particles called bosons. Now, the particles that make up you and me, they're called fermions, and they're kind of antisocial. They refuse to occupy the same space. But bosons, they're the opposite. They're happy to all pile into the exact same quantum state. And the result would be this fuzzy, transparent star held together by gravity. It might even be a giant, star-sized clump of dark matter.
So you're probably wondering, how on earth would you find something that might be literally invisible? Well, the key is gravity. A boson star would bend spacetime just like a black hole does. But, and this is a huge but, it doesn't have a hard surface or an event horizon, that point of no return. So it would give off a really unique signal in gravitational waves if it were to merge with something. They're definitely a dark horse in this race, but a really fascinating one.
And now for the ultimate challenger to the throne, the Gravastar. This thing was basically invented to solve all the weird problems with black holes. It just throws the whole idea of a singularity, that infinitely dense point, right out the window. Instead, it suggests there's a thin shell of matter surrounding a core of pure dark energy. Yeah, the same stuff that's pushing our universe apart. It's a seriously radical idea.
But here's the catch. From a distance, a gravastar would look almost exactly like a black hole. To prove one exists, we'd have to detect these incredibly faint gravitational wave echoes literally bouncing off its surface. It's a true long shot, mostly because, let's be honest, all of our current data on black holes fits the standard model just perfectly.
So at this point, you might be thinking, okay, this is cool, but why does any of this really matter? Finding a new kind of star is neat, for sure, but the stakes here are so much higher than that. This is about rewriting the fundamental rules of reality as we know it.
You see, this whole cosmic hunt is actually a proxy war. It's a battleground for the biggest, grandest ideas in all of physics, things like string theory and loop quantum gravity. These theories make huge claims about the nature of space and time and matter, but they are notoriously hard to test in a lab on Earth. But these exotic stars, they're the natural laboratories where the predictions of these theories get played out on a cosmic scale.
And here's where it all gets crystal clear. Some of these potential discoveries are what physicists call single-shot discriminators. They could instantly settle debates that have raged for decades. Like, for instance, if we find an axion star, something predicted by string theory, that's basically the first real piece of evidence for that entire framework. But on the flip side, if we find a Planck star, which is predicted by loop quantum gravity, that theory suddenly jumps to the front of the line.
Just think about that for a second. One single astronomical observation could do more to settle the biggest questions in physics than decades of work in our most powerful particle accelerators. The amount of scientific leverage we get from this search is just immense.
This search is literally going to write the next chapter of physics. We could find ourselves in a universe where dark matter is this active, creative force, building the first stars. Or maybe we end up in a universe where we finally prove that space-time itself is made of tiny, discrete little chunks. Or we could find nothing new at all, and those big questions just keep hanging there. The outcome of this cosmic hunt determines which textbook our kids will read.
And that's really the beauty of it all. You know, our particle colliders here on Earth, they might be struggling to reach higher and higher energies, but the universe? The universe has been running experiments at energies we can't even dream of for 13.8 billion years. The evidence, the results, they're already out there, just waiting for us in the sky. All we have to do is get good enough at reading them.
And in the end, that's what this is all about. It really doesn't matter how pretty or elegant a theory is. The only thing that matters is what the universe itself tells us is true. And right now, it's dropping some pretty big hints that the cosmic zoo is about to get some wild new additions.